All right, we are moving right along with our January 2020 exam, and now we are on to B-2. Now, B-2 is where we begin having to put our answers in the answer booklet. And you can see there's relative keys to what kind of information you need to include: big spaces, lines, short lines. Okay? The questions in B-2 should be relatively the easier of the written questions. Okay, so if you're finding yourself having to do multiple steps, probably looking at the question wrong. Okay, so I'm going to skip the reading. I can see the table. I'm going to go to the first question. State both the number of protons and the number of neutrons in an S33 atom. So S33. Okay, what else could I find out about S? If I go to the periodic table, I can see that it has an atomic number of 16. All right, so this 16 is the atomic number, and that is the number of protons. This 33, the mass number, is protons plus neutrons. So I would find neutrons by subtracting these two numbers. Okay, so my number of protons is 16, and my number of neutrons is 17. All right. In the space in your answer booklet, show a numerical setup for calculating the atomic mass. So I do not have to solve it. I just set it up. That is awesome because this is a complicated one. So let's kind of try to show these at the same time. All right. So the natural abundance and the atomic mass. So what I have to do is multiply the natural abundance, but not as a percent. I have to change it to a decimal and multiply it by the atomic mass, and then I would add up all those answers. So I would do 0.94, this is one way to write it, 0.9499 times 31.972. I would do that, right? Now this one, be careful, move it two places. It's going to be 0.0075 times 32.971. This one, be careful, as I'm going to need a 0 in front there, 0.0425 times 33.968. And then this one, again, be careful, 0.0001 times 35.967. And then what do I need to do with all of those? Add them up. So I could have written this plus like this. I could set it up like this, right? You have a few options, but this is basically the procedure, and this is probably how I would write it, like this, and this would give you your answer. Now, just real quickly, let's look here. Since this natural abundance is so high, that means on the periodic table, my atomic mass for sulfur should be closest to 32, which, look at that, it is. And it is a little bit bigger than 32. Why? Because these all have numbers bigger than 32. So the atomic mass on the periodic table should be between the smallest mass number and the largest mass number. And it is. Okay? Compare the energy of an electron in the third shell of a sulfur atom to the energy of an electron in the first shell of the same atom. Okay? The electron in the first shell has less energy than the electron in the third shell. Electrons that are closer to the nucleus in lower energy levels have less energy. Think about it. Smaller number, less energy. Okay, you can remember it maybe like that. All right, so now we had to turn the page here. We're going to flip our booklet here. And now these will give us 54 through 57. Okay, so I have some reading, I have diagrams, I have a data table. I'm just going to go to the question first because maybe I don't have to read it all, maybe I do. It says state evidence other than mass from the information given that the components of rock salt have different properties. So I have to ignore this. Okay, so let's start reading. During a laboratory activity, appropriate safety equipment is used and safety procedures are followed. A student separates a sample of rock salt that has two components, NaCl, solid, and small insoluble rock particles. First, the student thoroughly stirs the sample of rock salt into a sample of water in a flask. The mixture in the flask is filtered using the lab apparatus shown below. The water is evaporated from the beaker. The filter paper and its contents are dried. Okay, so what this means is that when the student added water and mixed it all together, that not everything dissolved, and some was able to be filtered on the filter paper. So what is evidence other than the information given that the components of rock salt have different properties? Some of the rock salt components dissolved in water, while others did not. Okay. Explain in terms of particle size why the rock particles are trapped by the filter paper. Okay, so in the filter paper, I'm pouring the liquid through, right? Some particles will be caught. Why, in terms of particle size, does that happen? The particles are trapped by the filter paper because they are larger than the openings or pores or holes in the paper. Okay, now 56, you see this bitty line, okay, should be a little line, a little answer. State the number of significant figures in the mass of the beaker with the dry NaCl. So right here, this one. How many significant figures? Well, there's a decimal point, so I start over here. Is this a 0? No, it is not. Count it, and now count everything. 1, 2, 3, 4. So my answer is just literally writing 4. Okay. 57, I got a big space. Let's see. Show a numerical setup for calculating the percent by mass of NaCl in the rock salt sample. Okay, so what I need to do is figure out, okay, let's look at the formula first. And we'll write it down. So percent composition by mass right here. So it's mass of part over mass of whole times 100. That's my formula. So let's go back. What am I doing in the rock salt sample? So my mass of part would be the mass of NaCl. The mass of the whole would be the mass of the rock salt. Don't forget to write the times 100. Okay, so I have the mass of the rock salt sample. Okay, so that's 16.4 grams. Keep the times 100. Now I need the mass of NaCl, and I don't have that here. What I do have is the beaker with dry NaCl and the clean empty beaker. So I had a clean empty beaker, and now I have some dry NaCl at the bottom. So how am I going to find the mass of just the dry NaCl? Well, I'm going to subtract those. So I'm going to do 240.0 minus 224.2. That will give me the mass of NaCl. And then stop. Don't have to do any calculations. I don't even have to do this subtraction. Don't give yourself an opportunity to make a mistake. Stop there. Done. That's it. Okay. Then we flip here and we will move on here to the next question set, which this next question set, oh, this has to do with gases. I'm guessing I'm going to have to do a combined gas law problem, but let's see. Compare the mass of the gas in cylinder A to the mass of the gas in cylinder B. Well, the mass of the gas in cylinder A is H2, and the mass in the gas in cylinder B is N2. So if I look at the periodic table, the atomic mass of hydrogen is basically 1. The atomic mass of nitrogen, basically 14. So 1 times 2 is 2. 14 times 2 is 28. So the mass of the gas in cylinder B is much greater, right? So the mass of nitrogen in cylinder B is greater than the mass of hydrogen in cylinder A. Okay? All right. State a change in temperature and a change in pressure that will cause the gas to behave more like an ideal gas. So do you remember ideal gases are very far apart, they're moving fast, rapid, random, straight line motion. So in order to be moving fast, what would the temperature have to be? It would have to be high. So increase the temperature, right? So increase temperature. That's what I would want to do. And what about pressure? Well, if I want the gas particles to be very far apart, I would have to decrease pressure. So gas particles behave most like an ideal gas at high temperature and low pressure. Okay? Now 60 has a bunch of lines again, so let's see. Explain in terms of collisions between gas molecules on the walls of the container why pushing the movable piston farther into cylinder B at constant temperature would increase pressure of the N2 gas. Well, here's what you have to remember. Pressure is created when gas particles bump into the walls of the container. Okay? So if I move the movable piston farther, that means I squish the space. Okay? So moving the piston would decrease volume. This would cause the gas particles to collide with the walls, of the container more. More collisions with the container equals more pressure. Okay. This was kind of just information, so I could probably have left this out. So this would cause the gas particles to collide with the walls of the container more. More collisions with the container equals more pressure. All right. Show a numerical setup for calculating the volume of the gas in cylinder B at STP. So now I know I have a combined gas law. Remember, I suspected that I did. And if you don't remember the combined gas law formula, then you go here. Combined gas law, right here. All right. So, cylinder B. So I'm focusing on cylinder B. So cylinder A and B are sealed rigid containers with movable pistons. Each cylinder holds 500 milliliters. So milliliters, that's what? So P1, V1, T1. I'm going to write it over here. I don't have to do it this way. I'm just going to do it this way to keep track of it. So the volume is 500 milliliters. That's volume 1. At 101.3 kPa. So that's pressure, 101.3 kPa. And 298 Kelvin. Okay, so that's where it is right now. And then it says I change it to STP. So what do? I look at my reference table, and here is information about STP. So the value for pressure is 101.3 kPa, and the value for temperature, I need it in Kelvin, right? 273 Kelvin. I have to use Kelvin with the combined gas law formula because I can't have anything negative, all right? Now V2 is what I'm trying to find. What do you notice? Well, I notice that pressure is the exact same, so I can leave it out, but it is not wrong to put it in, okay? I don't have to remove it, but I can. So let me show you what it would look like both ways. So 101.3 times 500. Oops, this should say T1. What did I write? V1. And that is 298 Kelvin equals 101.3 V2 over 273. And then I literally stop there. That's it. Done. I don't have to do a single thing. Okay? Or if I realize that the volume, that the pressure didn't change, I could leave it out of the equation. So I could just write 500 over 298 equals V2 over 273. I could just write it simply like that. And I don't have to do anything. You don't have to cross multiply. You don't have to rearrange the formula. All it says is show a correct numerical setup. This is the correct numerical setup. So this is a right answer, and so is this. You choose which one you would want to do. If you think leaving it out would confuse you, write it like this. If you realize you don't have to state this number, then you could leave it out and do this. That's up to you. Okay, let's move on to our next set of questions, which we have right here. I only have 2 questions for this section. State in terms of the concentration of ions why the 6.0 molar HCl aqueous is a better conductor of electricity than the 0.1 molar HCl aqueous. Okay. What makes something a better conductor if it has more ions? How do we have more ions? Well, sometimes it depends on the substance, but you can see in this case, it's the same substance. What else would affect the ions? Concentration. How do I know that's concentration? Big M, molarity, solution concentration. Okay, so why does the 6 molar HCl have a better conductivity? Because it has more ions. Remember, I have to talk about the concentration of ions. So 6.0 molar HCl has better conductivity because it has more ions. Period. That's it. Better conductivity, more ions. You can see 63, a short line, so that should not be a long answer. Identify the element in C6H12O6 that allows it to be classified as an organic compound. This is just a definition question. What element do organic compounds have to contain? Carbon. That's it. Okay, now I have 2 last questions in B2, so let's flip this way. Here they are. Nuclear. Complete the equation in your answer booklet for the decay of phosphorus 30 by writing a notation for the missing product. So now I go here and I have this equation and I need to put the missing product. Okay, so I need a top number, a bottom number, and a symbol. So the top number has to be the same on both sides. So I have 30, 0. So what does this have to be? 30, because 30 plus 0 is 30. All right, now let's look at the bottom. I have 15 on this side. This side I have a plus 1. So what would go here? I'd do 15 minus 1, which is 14. I can check that. 14 plus 1 is indeed 15. And now I need to go to my periodic table. Which number am I looking up? The bottom number. That's the atomic number. And I'm going to look up 14, which is Si. So there you go. This is what it should look like. And then I have a question, 1 left. Based on table N, determine the time required for an original 100 milligram sample of P32 to decay to only 25 milligrams of the sample remaining unchanged. So if I started with 100 milligrams, after one half-life, I would have 50. After another half-life, I would have 25. Okay, that's where I got here, right? So how many half-lives did that take? Remember, I count the arrows. That's 2 half-lives. I don't count this. This is just the starting point. Okay, half-life 1, half-life 2. But now I need to look up in reference table N, P32. So you have to be careful. You got to look up the right one. So P32, right? Phosphorus 32. Its half-life is 14.28 days. So this half-life takes 14.28 days. This half-life takes 14.28 days. So how much time does that take together? Well, I would add these up or think about multiplying that by 2, and that is going to give me 28.56 days. Okay, and there we go. We have finished up part B2.